All right, so the second part of 8.4 here deals with applications of these vectors. Okay, so these are going to be all story problem, physics type things. So all that setup in the work yesterday is going to help us do very practical and neat stuff with these guys here. So first thing is this picture here. So yesterday we said a unit vector is some vector v just divided by the magnitude, okay? So you literally just copy the vector. Magnitude is just like finding, it's like a Pythagorean theorem, okay? Now, if we take this equation and we solve it for v, well, we would multiply across by magnitude of v, and we get to this guy right here. Now, a unit vector, if we actually give it an angle here, okay? So we take this picture. Here's the I component, here's the j component, here's a circle with the radius of 1, because that's what a unit vector is, okay? Always has a radius of 1. So they're going in the direction, okay, but it only has a magnitude of 1. So if we tilt this up some alpha here, this vector has a cosine alpha component, and it has a sine alpha component, okay? And that's just like everything we've been doing this year with x's and y's, basically solving for the two components, the x and the y, to get to this guy right here. Now, if we say a unit vector is going to have some cosine alpha component in the I, plus some sine alpha in the j, and then we substitute this whole thing in right there, we get this equation. So we can say vector v is the magnitude of v times cosine of alpha I plus sine of alpha j. Okay, and it all just comes from that picture right here. So here's another little equation or formula, make sure you guys have down. So we're going to look at just two problems here. First one is a simple force problem. Okay, so a force of 10 newtons is applied in a direction that makes an angle of 45 degrees with the positive x-axis. Represent F in terms of I and J. So you'll typically see these like pushing a lawnmower, pushing down on a cart, something like that. Now, we're not sure which way this force vector is applied. Let's just assume it's going this way. So you're pushing straight up on something like this. Here's your alpha of 45 degrees. They're giving you the force with it. Okay, so that's directly giving you the magnitude. So this guy's got 10 newtons. Okay, write the force vector in terms of I and J. So we're just going to say, well, the force vector would be the magnitude times the cosine of alpha I plus the sine of alpha j. We already have the magnitude. We know that's 10 newtons. All we got to do is go plug in 45 degrees here in the I component, because that's what that component of the force is. Okay. Remember, there's two components to it. So in order to push on an angle here, you got one thing going this way, you got one thing going this way. Here's the vector that connects them both. So sine of 45 degrees j, and now we just have to evaluate this. So we use our yellow sheet. We should know sines and cosines of 45 by now. So 10 square root of 2 over 2i plus square root of 2 over 2j. Okay, I do want you to distribute this and simplify it a little bit. So this is 5 square root of 2i plus 5 square root of 2j. You can leave your answer like that. You'll probably see them in the back of the book, solution keys written this way, if they are the same thing. Oh, made that mistake twice now. 5 square root of 2 I plus j. Now be careful doing that last step. The only reason we could do that is sine of 45 and cosine of 45 are the exact same thing. If it was like 30, You may not be able to factor those out, so you may have to leave them in this form here. Okay, but if you're comfortable with it, you can write it in that last form as well. Okay, and that's literally it. So this is telling us there's two components. The total gives us a square root of 10. Gives us a magnitude of 10. There's 5 square roots of 2 in the I component. There's 5 square roots of 2 in the J component. Okay, now if we made a triangle with that, and you use Pythagorean theorem, this should turn into 25 times 2, 25 times 2. So this is the square root of 50 plus 50, which comes out as 10. Okay, so everything will work out to right triangles we've been looking at all year. Okay, there's all the work, kind of how the book does these things. All right, these suspension problems, okay, you can expect to have one on a test. They do take some time. Okay, so make sure you have a picture, you have some notes, you have some questions. Okay, if you've taken physics, you probably have a little bit of head start here on these, but we're going to go through these. So you get a box of supplies. Okay, it's got a weight and it's suspended by 2 cables attached to the ceiling. So what is the tension on each of the 2 cables? Okay, so one of the cables here makes a 30-degree angle. One of the cables makes a 45-degree angle. There's a box hanging from. Okay, hint here. Think about these force vectors. So we want to find the tension in the cable. Okay, so what's the force or what's going on in this thing here? Okay, how much of the weight is that holding? Well, this guy here has 2 different vectors. Gravity's pulling it straight down, and there's also an x vector here this way. Okay, and the rope is just the sum of both of those vectors. This 45 guy over here, gravity's pulling this perfectly down this way. There's also a x component being pulled in, and it gives us the sum of this guy right here. Okay, this box is doing nothing but being pulled straight down. Okay, so what I'm going to do is transfer the picture over to something like this. Okay, so there's 3 different vectors or forces going on. So with those 3 forces, okay, clearly the box is just hanging there. So that's what we call static equilibrium. Okay, so the forces are kind of canceling each other out. So one's not winning over the other. Okay, it's staying in perfect balance. So the sum of all the force vectors should be 0. Well, there's 2 different components to them. There's I's and there's J's. Okay, so we need to look at each one separately. So the I's balance the I's out, and the J's balance the J's out. Okay, whatever this box is being pulled down, the cable tension in the J component is balancing that out. Okay, if they weren't strong enough, obviously that box would fall down. So here's what we got to think about. We go back to our picture. Okay, this guy's being pulled at a 45-degree angle. So by alternate interior angles, if you assume the ceiling and the box are parallel, we know that's a 45-degree angle as well. Now, this guy was being pulled at a 30. So by alternate interior angles, this is 30 degrees. But if we reset kind of the static equilibrium point, this thing really right here is 150. So we have to consider it that way. All right. So let's call this guy force 1. Let's call this guy force 2. Let's call this guy force 3. So those 3 things got to cancel each other out. Okay? So if we start writing some equations now. Force 1, actually, let's just bring this over to a part 2, and we'll start with some equations.